So how does an AI actually think ahead? When it's looking at a really complex problem, how does it figure out that perfect sequence of moves to get to the solution? Well, it all comes down to one of the most foundational ideas in all of artificial intelligence, a super powerful technique called search.
I mean, really think about it for a second. When you pull up your GPS and it maps out the fastest way to get somewhere in just a couple of seconds, that's not magic. Or when you see a character in a video game flawlessly navigate a tricky maze, it's not just following a pre-written script. In both of those cases, what you're seeing is an intelligent agent exploring a massive world of possibilities, using this process of search to find a path from A to B.
All right, let's get into it. Before we can ask an AI to solve a puzzle, we have to describe that puzzle in a language it can actually understand. We have to give it structure. We're going to be talking about what are called problem-solving agents. Just picture an AI that's working in a nice, simple world, a world where it can see everything, where all the rules are known, and when it takes an action, the result is totally predictable, no surprises. Okay, so to turn any puzzle into something an AI can chew on, we need these 4 ingredients. First up, the state space. This is literally every single possible situation the agent could find itself in. Then we have the successor function. Think of this as the rulebook. What moves can I make, and what happens when I make them? Third, the start state. Super simple, this is just our starting line. And finally, the goal test. This is just a yes or no question. Are we there yet? A solution, then, is just the recipe of actions that takes us from that start state to a state where the goal test says yes.
This Pac-Man example is perfect because it shows how one tiny change to the goal can make the problem explode in complexity. Look, if the goal is just get to this spot, the state is easy. It's just Pac-Man's XY coordinates. But if the goal becomes eat all the food, whoa, now a state isn't just Pac-Man's location, it's his location plus the on or off status of every single food pellet on the board. This is why getting the problem definition right is absolutely the most important first step.
To make all of this really stick, we're going to use one single example for the rest of this explainer, finding the shortest drive from the city of Arad to Bucharest in Romania. So let's frame it using our 4 ingredients. The state space is all the cities on the map. The start state, obviously, is Arad. The goal test is simple. Is our current city Bucharest? And the successor function, that just tells us which neighboring cities we can drive to and, crucially, the distance to each one.
Now, this is a really important distinction to make. The state space graph is like the actual paper roadmap of Romania. Every city is a dot, every road is a line, and each city only shows up once. It is the problem. The search tree, on the other hand, is the story of our agent's journey. As it starts exploring paths from Arad, it builds this tree of possibilities. And a city like Sibiu might show up multiple times in the tree if there are a few different routes to get there. So remember, the graph is the map, the tree is the journey.
This brings us to a huge potential trap in search. What happens if our agent drives from Arad to Sibiu and then just turns around and drives right back to Arad? Or worse, what if it gets stuck in a loop just driving around a few cities over and over again, forever? If the algorithm has no memory of where it's already been, it can get stuck in these cycles, building a search tree that's infinitely big and never, ever finding a solution.
So how do we stop our AI from driving in circles? Well, smart algorithms use a really simple but powerful idea. They give it a memory. It's often called an explored set or a closed list. Basically, it's just a list of every place the algorithm has already visited and checked out. So before it adds a new city to its plan, it asks a quick question. Wait, have I been here before? If the answer is yes, it just throws that path away and moves on. This one little trick saves it from infinite loops and makes the whole process way more efficient.
Okay, so we've got our problem all set up, and we know how to keep our agent from getting lost in loops. Now for the big question. How does it actually decide which road to take next? We're going to look at 2 basic strategies called uninformed search. And uninformed just means the agent has no clue how close the goal is. It's kind of like searching a maze in the dark with only a map of your immediate surroundings.
Let's meet our 2 searchers, depth first search, or DFS, and breadth first search, BFS. I like to think of them as having totally different personalities. DFS is the impatient, hyper-focused one. It picks a direction and just goes. It dives as deep as it can, hoping it gets lucky. BFS, on the other hand, is the cautious and methodical one. It carefully checks every single door in the current room before it even thinks about stepping into the next one.
So the strategy for depth-first search is always to explore the deepest possible path first. Let's go back to our trip from Arad.
DFS might immediately pick the road to Sibiu, then from Sibiu it goes to Fagarash, and from there, it just keeps going deeper and deeper down that one route. It's only when it hits a dead end, or hopefully the goal, that it backtracks to the last city where it had a choice and tries the other road. It's a dive deep, then backtrack kind of approach.
Now, the piece of code that makes DFS work is something called a LIFO queue, but you probably know it as a stack. LIFO means last in, first out. The best analogy is a stack of plates. You add a new plate to the top, and you take a plate from the top. In DFS, every new city it discovers gets put on the top of the stack, and since it always pulls its next destination from the top, it naturally keeps exploring the newest, deepest path it just found.
So, what are the pros and cons of this approach? Well, it's complete, which means as long as we stop it from going in circles, it's guaranteed to find a solution eventually. But, and this is a big but, it's not optimal. It'll find a path, but there's no guarantee it's the best one. It might find a super long, winding route just because it was the first one it stumbled on. Its biggest superpower, though, is its memory usage. It only has to remember the one path it's currently on, which makes it fantastic for problems with a massive number of states.
All right, let's switch gears and talk about our other strategy, breadth-first search. BFS is pretty much the polar opposite of DFS. Its whole game is to expand the shallowest node first. So starting from Arad, it doesn't just pick one road and go. Nope. It first looks at all the cities directly connected to Arad, Sibiu, Timisoara, and Zarind. Only after it's put all of those level 1 cities on its list does it then move on to look at all of their neighbors, the level 2 cities. It explores the map in these systematic expanding rings.
The engine behind BFS is a FIFO queue, first in, first out. And the perfect way to think about this is a line at a grocery store. The first person to get in line is the first person to get checked out. With BFS, when it finds new cities, it adds them to the back of the line. It always works on the city at the front of the line, which is guaranteed to be the oldest, and therefore the shallowest, when it hasn't checked out yet. This is what enforces that level-by-level exploration.
So how does our cautious friend BFS measure up? Well, it's complete, and it's also optimal, but with one major catch. It will always find the path with the fewest steps, which is only the shortest path if every single step has the exact same cost. But its biggest weakness, its Achilles heel, is memory. Because it has to keep track of every single node on every level it's exploring, the amount of memory it needs can absolutely explode on bigger problems.
So this is the problem, right? BFS finds the route with the fewest cities, but we wanted the shortest distance. The roads on our map have different lengths. What do we do when our actions have different costs? Well, this brings us to a much smarter algorithm, Uniform Cost Search, or UCS.
Uniform Cost Search takes the methodical idea of BFS and makes one simple but brilliant change. Instead of expanding the shallowest node, it expands the node with the lowest total path cost from the starting point. It does not care one bit about how many steps it took to get there, it only cares about the total mileage. You can picture it spreading out from the start city not in rings of equal steps, but in rings of equal cost.
Let's trace this on our Romania map, because this is where it gets cool. From Sibiu, UCS finds a path to Bucharest through Fagaras and calculates the total cost, 310 kilometers. Now, a simpler algorithm might stop there, but UCS doesn't. It looks at its list of places to explore and sees another path, through Râmnicu Vâlcea, that so far only costs 177. It's cheaper, so it explores that one next. It follows it through Pătesti and finds a new path to Bucharest that only costs 278. And here's the key. Only when the cheapest path on its entire to-do list is the one that leads to the goal does it stop and declare victory.
And the special tool that makes this possible is called a priority queue. It's like a regular line, but every person in the line has a number showing how important they are. The queue automatically makes sure that the person with the highest priority, which for UCS means the lowest path cost, is always at the front, ready to go next. This is how UCS always knows to work on the cheapest known path, no matter how deep or shallow it is. So when we look at UCS, its superpower is crystal clear. It is complete, and it is absolutely guaranteed to find the path with the lowest total cost, period. But what's the price you pay for that guarantee? Well, it's complexity. Because UCS has no sense of direction, it just explores outward in every direction based on cost. It can waste a lot of time and memory exploring paths that are actually leading it further away from the goal.
Whew, okay. We've just covered 3 really powerful fundamental search strategies: depth first, breadth first, and uniform cost. Each one has its own style, its own strengths, and its own weaknesses. So if you're the one building the AI, how in the world do you pick the right tool for the job? Let's break it all down in one final comparison.
And this table really brings it all home. Look, if your number one concern is running out of memory and you just need an answer, not necessarily the best one, DFS is your go-to. If all your steps cost the same and you want the solution with the fewest number of moves, BFS is your perfect match. But if the costs are all different and you absolutely must find the cheapest possible solution, you have to go with UCS. There's no single best algorithm here. It always comes down to the problem you're trying to solve.
You know, everything we've talked about today falls under uninformed search. These agents are basically searching blind. They have the roadmap, but they have no idea if the destination is north, south, east, or west. And that leads to a really interesting final question. What if our agent had a hint, a nudge in the right direction? What if it knew that Bucharest was generally to the southeast of Arad? How would that completely change the game? Well, that is the secret to the next level of AI planning, informed search. But that's a story for another time. Thanks for joining me.